So now we'll move on to calculations involving the normal distribution, and specifically like probabilities and stuff. So let's think about the normal curve, for example, here. And as I said, for a continuous random variable, the probabilities are areas. And so we would have to do an integral. But the normal distribution formula isn't something we can integrate very easily, or really with ACE level skills at all. So that's why they provide something called the table of Z values. And this specifically gives you all the areas between negative infinity and some positive values. And this is for the distribution of the random variable Z. This is what Z is, a special variable for this special distribution. It's normal for the mean of 0 and the variance of 1, which also means the standard deviation will be 1. And this is called the standard normal. So for example, for standard normal, for the standard normal distribution, if we wanted to know x's probability of x is less than 1.213, we go to this table. We start with 1.2. When we do 1, to add the 1, and then for the 3, we go all the way along, 1, 2, 3, so then we do 0.8869, and then add the 6 on the end. If it was, say, a 15, we would do that. But then anyway, this is that probability. Obviously, if you had to do p, x is greater than, you'd do 1 minus 0.8875. Now, what about negative values? Say, p is x is less than or equal to negative 1.103. Now, I do that less than or equal to deliberately to tell you that less than or equal to or less than, it doesn't matter because it's continuous. And it goes the same for greater than or equal to. Doesn't matter because it's continuous. So here it tells you, now this is another thing, in a standard normal, the probability of x is less than a certain z is equal to phi, the Greek letter phi, which is the symbol of z. And that's what we're doing here. So it's asking, so this here would be phi of minus 1.103. And it's saying that if we have a negative, we can just say that it is equal to 1 minus the phi of the positive version of it. So then let's practice with our z's. I'll rub this out so we can do this a bit easier. 1.1. Then we do O. Then we need to add 3. So it becomes 0.8649. And then if you evaluate that, then you get that. And the reason why this works is because the normal distribution curve is symmetrical. So on negative something has the same area to the left as positive something has to the right. And this also means it has the same area to the right as the positive thing has to the left. It's symmetrical. If it helps, you may want to do a sketch. That can always be helpful. So you know what areas to minus and stuff. So that's with the standard normal. But as we know, it's not this easy. Because not everything will have a mean of 0 and a standard deviation of 1. You think the mean height is 0 centimetres? No. So what if we had something such as, I'll do small numbers for now. X is distributed normal mean of 9 and of standard deviation of 3. So if I draw up axes here, this is a horrible drawing, by the way, and we're saying this is a standard normal, that's 0. So when we have, okay, let's, I've made the same mistake that I told you guys not to make. The parameters for a normal distribution is the mean and the variance, but I very foolishly just did it as a standard deviation. Let's say the mean, the variance is 9, so that means sigma equals root 9, which is 3. So it's standard deviation 3. So we're increasing the standard deviation threefold, which means we will first make it a third the height and 3 times as spread out. So it becomes more like this. Again, apologies for the drawing. And then for 9 of the mean, we would shift this along, translation, to be 9. So what if we want to go back? Like, so we're trying to do Px is less than 10. What if we want to go back? Well, what we do is we do 10. We just do the reverse BEDMAS. We do 10. We subtract the 9. And then we divide by 3. And then that'll get us back to a normal curve. So that's why the value for z, which is the thing that you use to work out the probabilities in the normal, is equal to x minus mu over the standard deviation. And this step is called standardising. And you need to do that. Additionally, what if you wanted to do p minus 1.07 less than x less than 2.1? Well, you would just do the probability of being less than 2.1 and subtract the probability of being less than negative 1.07. I think that's obvious, but what may not be obvious is this bad way of writing this. What this means actually is, and we're still looking, it doesn't matter if I'm doing the standard or normal, standard or not standard, I'm just doing it as a way of saying this, say this is negative 1.07, what this is saying is, and then this is 2.1, it's asking for this probability, so this would be equal to phi of negative 1.07, but then you'd have to add 1 minus phi of 2.1 because you're adding the probability that it's greater than 2.1. That makes sense. Again, sketch a curve and then shade in the things you need to do, and then you can kind of see what you need to minus and what you need to add. So say if you were given something like x is distributed in 3 and 49, find p. X is less than 5. What you would first do is you do your z, 5 minus 3, and then divide by root of 49. And then you get some decimal, and I say do it to 3dp. Then put it in the table, and then figure it out. We will continue with more normal distribution calculations in the next video.